whenever we have a series that converges, we can estimate the sum of the series by taking longer and longer partial sums. And we know that the limit of the sequence of partial sums is going to converge to the sum of the series, right? In the case that we have a series that satisfies the alternating series test, then we'll actually be able to estimate how far off our partial sum is from the actual value of the sum of the series. We'll be able to come up with an upper bound. So we need to have that we have an alternating series. We need that the terms, the size of the terms is getting smaller, and that the limit of the terms is equal to 0. So these conditions guarantee that we have a convergent alternating series. This theorem says that the remainder, this is all of the pieces that we're missing, that is, all of the terms that we haven't included in our sum. The size of this error is less than Pn plus 1, the next term's magnitude. So if we add up the first n terms, the difference between the actual sum of the series and our estimate is less than just the next term's magnitude. All right, and I'm cursing the notation from the book. So they are mixing their ends together. So notice that this has changed. So here k is going to be my index throughout, and n is equal to the, this is how many terms we've added up. Okay, so what we're saying is that the difference between our sum, which is just the sum of the first n terms, and the actual value of the sum is less than just the n plus first term's magnitude. Let's see this in an example. In this problem, we want to estimate the sum of this series, and we want our estimate to be correct to 3 decimal places. So our solution is going to have 2 steps. First, we're going to show that our series is convergent using the alternating series test. Then we're going to work out how many terms we need to add together to guarantee that we have a sum that is within the given error bound. So we're going to use the alternating series estimation theorem to find the n so that the nth partial sum is correct to 3 decimal places. Let's get started. All right, so we're going to try this out by finding the sum of the series from k equals 1 to infinity of -1 to the k over k cubed, correct to 3 decimal places. Okay, so we're going to use the alternating series test. This thing is definitely alternating. If we take the limit as n goes to infinity of 1 over n cubed, we get 0. So indeed, we satisfy the second condition. And f of x equals 1 over x cubed is a decreasing function. So in particular, f of n plus 1 is less than f of n for all n. So we satisfy the third condition. All right, these 3 things taken together tell us that our series converges. All right. Okay, so we want to estimate this sum of the series, and we want our estimate to be guaranteed to be particularly good. So in particular, we want that the difference between the actual sum of the series and our sum of our finite sum is supposed to be good to within 3 decimal places. Alright guys, so to be honest with you, we have computers to sum things. We can sum all day long. So we're not going to be that picky about making sure that this is correct to 3 decimal places. I'm going to say let's make sure that this error is less than 0.0000001. How about that? Okay. This will definitely be correct to 3 decimal places. Whoops, and this is supposed to be a subtraction, not an addition. So we want that the difference between the actual sum of the series and our sum is less than this big number. Okay, well, to guarantee this, what we're going to do is use that estimate from the alternating series error estimate. So the difference between these two things is less than the nth term. So this is going to be less than 1 over n plus 1 cubed. I think I said the nth term. I mean the next term, the term that gets left out here. So the last term that we're adding up here is the nth term. So the difference is going to be less than 1 over n plus 1 cubed. And we want to guarantee that this term is less than 0.0000. So many zeros, 1. Okay. And the reason for that is that it's not so bad to find an n that is satisfies this inequality. So we're going to find such an n, and that'll tell us how many terms we need to add up to make sure that we can satisfy this inequality, and that will definitely 100% make sure that we are correct to 3 decimal places. Great. Let's do it. Okay, so we want 1 over n plus 1 cubed to be less than 1 over, and there's 1, 2, 3, 4, 5, 6. 1 over 10 to the 6th. Okay, so in particular, we want n plus 1 cubed to be greater than 10 to the 6th. Okay, so n plus 1 should be greater than 10 squared. And n is going to be greater than 99. Okay, so let's choose n equals 100. This is so overkill, guys. But it doesn't matter because we're going to be using, we'll just plug this guy into Desmos. It'll calculate the sum for us in no time at all. I'll show you how in class. Okay, so let's take a look at what is the sum from 1 to 100 of -1 to the k over k cubed. Something like 12 works. But let's check this out. All right, with the power of modern computing, we have that this is equal to -0.90154,218. Okay, and here we can guarantee that these first 5 decimal places agree with the decimals in the actual sum of the series. Okay. All right, so the alternating series estimation theorem gives you a contract, a guarantee of how accurate your partial sums are. We can use computers to calculate partial sums with lots and lots and lots of terms. But it's very useful to have some way of guaranteeing that what we're seeing is not very, very slow growth, that we're actually seeing convergence on the value of the series.